Assalamu alaikum guys. I hope everyone is fine. We will start the class in few minutes. I'm just waiting for the students to enter into the class. At present, we have 23 students. So we will just wait few more minutes before we start the class.
ओके सर, वो 2-3 स्टूडेंट्स रहते हैं, उनकी ईमेल्स को काइंडली ऐड कर दें।
एक सेकेंड, मैं आपको जवाब शेयर कॉपी द मीटिंग लिंक। जवाब मैंने ना आपको ये लिंक सेंड किए।
यस सर।
जो लोग नहीं है उनको कहो कि इसको क्लिक करके आ जाएं।
ओके सर।
और आपने वो मुझे ना शाम को आपने रिमाइंड भी कराना है। मैंने आई विल ऐड देम इन द टीम्स, ठीक है, एमएस टीम्स। वैसे उनका नाम क्या है? रोल नंबर बताते हैं उनका? Okay, guys, I think we should start now. Okay, ji, Bismillahirrahmanirrahim. Let's start with our today's lecture. So last time we have studied about the introduction of the subject. We have studied about the CLOs, PLOs. We have studied about general terms like different types of forces, normal forces, shear forces, bending moment, torsion. Now today we will start with the stresses. As the name of the chapter indicates, so the name of the chapter is plane stress transformation. I am following R.C. Hibbeler. I am following R.C. Hibbeler 8th edition. It's chapter number 9. I can share the link of the book as well, and if you do not have the book, you can download it from here. So for the what you say, for plane stress, we will be following chapter number 9, and for plane strain, we will be following chapter number 10 of R.C. Hibbeler 8th edition. In a short while, the book will be uploaded to this group as well. Moreover, I have also uploaded this book on OneDrive, and I will share the link of that file with you. On the other side, you can download it directly from this message. See, the book has been sent. ठीक है जी, R.C. Hibbeler 8th edition, chapter number 9 and chapter number 10. So at present, we are following chapter number 9 for plane stress transformation. So let's start. So first definition which we need to study today is normal stress. So normal stress, it is represented by sigma. So normal stress is the intensity of the force acting normal to the applied area. Just to recall, stress is equal to force per unit area. So you have normal forces which act perpendicular to the area, and these forces will either produce, tend to push or pull the body. ठीक है जी, push or pull means they are either compressive or tensile forces. So correspondingly, normal forces will produce normal stresses, compressive stresses or tensile stresses. Then you have the shear force, the force which lies in the plane of the area, and this force basically tries to cut the element into two halves. So shear force will stresses. So the intensity of the force acting normal to the applied area is defined as normal stress. If the normal force or the stress pulls on the applied area, if you apply the force which is a pull force, which is producing a tension in the body, that will result in tensile stresses. It is referred to as the tensile stress. Stress is equal to force per unit area. Area is area remains same. So with the variation or with the change in the applied force, your normal stresses will change. ठीक है जी. So if the normal force or the stress pulls on the applied area, ठीक है जी, if the normal force or the stress pulls on the applied area, it is referred to as a tensile stress. Whereas if the normal force or the stress pushes on the applied area, means it tries to reduce the area or contract the element, that will result in a compressive stress. In general, tensile stresses which are producing the pull in the body, which are trying to elongate the body, they are considered as positive stresses. And compressive stresses which are trying to shorten or contract the body, they are called as compressive stresses. They are negative in nature. Fine. So we will represent tensile stresses with positive sign and compressive stresses with negative sign. Then comes the shear stress. Shear stress, it is represented by torque. Shear stress is represented by torque, and shear stress is basically the intensity of the force acting tangent to the applied area. The intensity of the force acting tangent to the applied area is called as the shear stress. Fine. So in our further discussions, we will limit our discussion to normal stresses and shear stresses. So that's why it's very important that if you have any question about the normal force, normal stresses, shear force, and shear stress, you can ask me now. Because whole of this chapter is about the computations of normal stresses and the shear stresses acting on the element. Ji. If no question, then I am proceeding forward. Now, next thing is this is a body. ठीक है जी, this is a body, and you can see these are the external forces acting on it. P1, P2, P3, P4. This is one arbitrary point selected O. ठीक है जी, one point is selected. Now there are two sections have been cut. One section is section AA. So the section is cut like this. ठीक है जी, resulting into this shape. Then the second plane is BB. The section is cut about this BB section, and it results into this shape. Now the question is that whether we will get the same resultant stresses, we will get the same resultant stresses in both these two cases. What do you think? Will we get the same normal stresses and shear stresses in case B and case C, where your plane is AA and in this case the plane is BB, and both are passing through an arbitrary point O, where we want to calculate the resultant stresses? G.
No, sir, they will not be same.
Correct. So first, these are our reference planes, AA and BB. So stresses acting at a point in a body depend on the orientation of the reference plane. So orientation of this reference plane, that will determine, ठीक है जी, the orientation of the reference plane will determine the normal and the shear stresses acting on the resultant shear stresses and normal stresses acting at the selected point. So stresses acting at a point in a body depend on the orientation of the reference plane. Means that if you want to find the stresses in an element at an angle theta 1 or theta 2 or theta 3, let's say theta 1, theta 2, theta 3 are different orientations. So what will happen? You will get the pair of stresses. Pair of stresses means you will get the normal stresses and the shear stresses that will be different from one another. So the two sets of the stresses that we will get from plane AA and plane BB, the two sets of the stresses, they will not be equal, although they are computed at the same point. ठीक है जी, they are computed at the point A, point O, point O. So the two sets of the stresses would not be equal, although they are computed at the same point, because the resultant forces acting on the two planes, plane AA and plane BB, they will not be equal. ठीक है जी. So in over cases, what we will do, we will calculate the normal stress. This sigma is over normal stress, tau is over shear stress. So you can see the normal stress is basically trying to pull the element, and then this shear stress, it is trying to cut the element into two halves, or the stress, which is basically force which tries to slide one part of the element over the other. So the two sets of the stresses will not be equal. So it means that normal stresses and the shear stresses, they are dependent on the orientation of the reference plane. In other words, I can say that the normal stresses and shear stresses, they are dependent on the theta, orientation of the element. Fine, is this point clear, guys?
सर स्ट्रेस इसलिए भी वेरी कर रहे हैं क्योंकि दोनों सेक्शंस के लिए एरिया वेरी कर रहा है.
आई डिड नॉट गेट इट, थोड़ा सा आखिर में मैं आपको क्वेश्चन मिस कर गया.
सर स्ट्रेस इज आल्सो डिपेंडेंट ऑन द एरिया ऑफ द बॉडी ना, तो दोनों सेक्शंस में
at present we are keeping the area as the same. ठीक है जी, एरिया सेम है एलिमेंट का. area, we are keeping the area same. When I say theta 1, theta 2 and theta 3, these are the three different orientations of the element. In that case, I am basically considering that the area will remain same. So the two sets of the stresses would not be equal, although they are computed at the same point, because the resultant forces acting on the two planes, they are not equal. So basically it's the resultant force which is changing. ठीक है जी. So because the resultant forces acting on the two planes will not be same, so hence the stresses acting on the two planes, they will not be same. Fine. So point to be noted here is that with the change in the reference planes, uh, normal stresses and shear stresses, they will change. So the set of normal and shear stress will change with the change in the orientation of the reference plane. So later on today we will derive the equation that if we are given this normal stress, let's say this normal stress and shear stress, and I want to calculate the normal stress and shear stress at any other orientation, then I can link this normal and shear stress with the orientation theta. So if I just know the orientation, I can calculate the transformed normal and shear stresses. I can calculate the transformed normal and shear stress. Now, next thing is stresses at any arbitrary plane. It is usually not practical to directly compute the stresses acting on arbitrarily chosen planes. Why? Because the available formula gives stresses on certain reference planes only. ठीक है जी, as you know that at present I think you have studied two theories. You have studied the Flexure theory, you have studied the shear theory, and in both these theories you had made some assumptions. ठीक है जी. So the Flexure formula is limited to the normal stress acting on the cross-sectional plane of the beam. ठीक है जी. So flexure formula is only limited to the normal force acting on the cross-sectional plane. Fine. Similarly, the shear stress formula. Shear stress formula, which you have studied for the shafts and for the beams, it is only applicable to the cross-sectional and the longitudinal plates. It is only applicable to cross-sectional and longitudinal plates. So let's have a look at this flexure theory or flexure formula. Flexure formula is stress sigma. This is flexural stresses. M is the applied bending moment. I is the moment of inertia. Y is the distance of the fibers from the neutral axis. So basically your flexure stresses will be directly proportional to the distance from the neutral axis. As you move away from the neutral axis, your flexure stresses will start increasing. Fine. And as you know that the flexure stresses, they will be minimum at the neutral axis and they will be maximum at the extreme fibers. Fine. So flexure stress sigma is equal to my over I. The point to be noted here, that this flexure formula is only limited to the normal stresses or the forces acting on the cross-sectional plane of the beam, acting on the cross-section plane of the beam. Similarly, the shear stress. This is the shear stress formula. This shear stress formula you will study in more detail in this subject as well. You will also study how to calculate the shear flow, how to calculate the shear center. So shear stress tau is equal to VQ over IB, where V is the shear force, Q is the first moment of area, I is your moment of inertia or second moment of area, B is the width of the section. Fine. So I repeat this, it is usually not practical to directly compute the stresses acting on the arbitrary chosen planes because each formula is applicable on certain reference plane. ठीक है जी? For example, the flexure formula is applicable to the normal forces acting on the cross-sectional plane of the beam. Similarly, the shear stress formula for beams and the shafts, it is only applicable to the cross-sectional and longitudinal planes. Now, let's take an example that how we are going to calculate the normal stresses and the shear stresses in our cases. ठीक है जी? So this figure is shown, so I want to explain this figure. Uh, this is one element. Fine. If we want to do the finite element modeling, in finite element modeling, what will happen? That this element will be split into smaller number of units, just like this one unit. So what the computer system will do, they will analyze each such element and then the results will be converged to one point. So then you will get one value of the normal stress and the shear stress. Fine. In the theoretical calculation or manual calculation, what we do, uh, similarly to that, we have split the element into number of sub elements, and we are going to select one such element which is the true representative of this element. This is sub element which is true representative of this element. Now, if you see this, this is a three-dimensional element. In this three-dimensional element, normal stresses are acting. Normal stresses are basically produced by the normal forces, which are basically trying to apply the pull, means trying to elongate, or trying to push, or trying to contract the element. ठीक है जी? So this is an element, and these are the normal stresses. Sigma. This represents the normal stresses. Fine. Then you have these shear stresses have been shown. Shear stresses are those stresses which will try to slide the element, one a part of the element over the other. ठीक है जी? And if we draw this three-dimensional element, in two-dimensional element. At present, I'm just giving you overview. We will go uh, in depth today. ठीक है जी? One we will be doing over derivation. ठीक है? At present, we just want to know what is normal stress, what is shear stress. So this is the what you say two-dimensional view of the element. You can see this is the normal stress, fine, and these are the shear stresses. This is the shear stress, ठीक है जी? And these shear stresses they are trying to innovate as well, ठीक है जी? So So this was just very simple. Now we will come to the main point that how normal stresses and shear stresses they are produced and how they can be computed in manual calculations. Now, in general, this is your three-dimensional element. Three-dimensional element. So this is my x-axis, this is my y-axis, and this is my z-axis. So in three-dimensional element, this is my x-axis, this is my y-axis, and this is my z-axis. So now I have three-dimensional element having six faces. Face 1, ठीक है जी, this is phase 1, let's say phase 1, and opposite to this is phase let's say this one, phase 2, this one. Then you have this phase 3, and opposite to this you have this phase 4. You can see this these uh, shear stresses and normal stresses they have represented with what you say grayish color line. Can you see this?
Yes, sir.
Now, yes. Now, similarly, you have this phase 5, and you have these normal and shear stresses, and on the phase 6, this one, bottom one, you can see these grayish lines which are representing the complementary normal stresses and the shear stresses acting on the plane. Now, if I divide these six faces, this is my XY plane, this one. This bottom plane is my X and Y plane. Okay, this is my XY plane, this bottom one. Similarly, this my top one will be X and Y plane. Okay, this will be X and Y plane. So whatever will be the magnitude of the normal and the shear stress which is acting on the what you say top of the XY plane, the same stresses will be acting at the bottom of the XY plane. ठीक है जी? So that the element is in equilibrium. Fine. Now, similarly, this is my what you say Z, this is my Z, and this is my Y. So this is my YZ plane. So whatever the stresses, normal and shear stresses, which are acting in this YZ plane, which is the front side, the same stresses will be acting on this face, which is on the back side. This one. ठीक है जी? This one. Fine. Similarly, this one is my X and Z phase, X and Z phase, and this is the normal stress, this is the shear stress. So whatever is the normal and the shear stress, which is acting on this X and Z plane, the same stresses will be acting on this X and Z plane, this one. ठीक है जी? So it means that if we can calculate if we can calculate the normal stresses and the shear stresses on the three faces, ठीक है जी? Then basically the other three faces, the normal and the shear stresses are basically complementary stresses. So in the computation, I just need to know the normal stresses and the shear stresses which are acting on this uh, YZ plane, ठीक है जी? The normal and the shear stresses which are acting on this X and Z plane, normal and the shear stresses which are acting on this XY plane. So everyone agrees with me up till this point?
Yes, sir.
Okay. Now we will proceed further. Now you see this, stresses are basically represented by two subscripts. Stresses are represented by two subscripts. ठीक है जी. Now, what are our normal stresses? Normal stresses are produced by the normal forces, which basically try to apply the pull or the push on the element. Now, over normal stresses is this one, sigma y, because it is acting along the y direction. So sigma y, normal stress sigma y. Actually, it should be sigma y y, but it is, normal stresses. They are represented by one subscript. But even if you will represent it with two subscripts, it will be sigma y y. So it's the same. So normal stress sigma y. Then you have this normal stress sigma x. This is acting along the x direction. This is acting along the x direction. Then you have this sigma z. It is the normal stress sigma z. It is the normal stress which is acting along the z direction, sigma z. So now on this element, there are three normal stresses. There are three normal stresses, sigma y, sigma x, and sigma z. Everyone agrees with this? Now, the next thing is the shear stresses. Shear stresses. Now, if you see on each face, there are two shear stresses they are acting. ठीक है जी. On each face there are two shear stresses are acting. Now we have to first designate those stresses. Now first let's consider this face ZY or YZ plane. Okay. Now see how they are representing the shear stresses, because first we need to understand the designation. So in this designation we will follow first subscript. So as I am saying that the stresses are represented by two subscripts, you can see this, two subscripts. The first subscript will represent the plane name. The first subscript will represent the plane name. ठीक है जी. If your stress is acting in the x plane, then first subscript is x. If it is acting in the y plane, then the first subscript will be y. If it is acting in the z plane, then the first subscript will be z. Then the second subscript represents the direction in which the stress is acting. The second subscript represents the direction. The second subscript represents the direction in which the stresses are acting. ठीक है जी. So in the case of the shear stress, it is designated by two subscripts. Subscript 1 represents the plane name. Subscript 2 represents the direction of the stresses. Direction of the stresses. Fine. So let's see how we are naming. In the book, they are not following this, what you say, this sign convention by hard and fast rule, but in over calculations, in over computations, we will strictly follow this, that the first subscript represents the plane name, the second subscript represents the direction of the stresses. Okay, so now we have this. First, let's designate this shear stress and this shear stress. It is acting on the y plane. It is acting on the y plane, and this stress is acting towards the x. So it is basically tau yx. This is basically tau yx. ठीक है जी? Then, in fact, we should start with this. This is exactly the same as over sign convention. So this is normal stress, no issue. The shear stress. So this shear stress, these are in the x plane. ठीक है जी? You can see this. This shear stress, this is your x. This is your x. So these are in your x plane, and first subscript is x in both the cases. First subscript is x in both the cases. Now this shear stress, it is acting upwards towards the z direction, So this shear stress has been designated as tau xz, tau xz. This one, this is tau x, and it is acting in the y direction. It is acting in the y direction. So this stress will be, shear stress will be tau xy. Do you understand this, guys? This one, tau xz and tau xy. If you have any question, please ask me now. It's clear?
Yes, sir.
Okay. Now comes this phase. On this phase, you have two shear stresses. This is now y plane. The plane is y. The plane is y. The plane is y, and the direction of this stress is tau. This direction of this stress is in x-axis. So this will be tau yx. Tau yx. ठीक है जी? And this one will be tau yz. Tau yz. Similarly, in this case, it is now in the z plane. So in the z plane, this one which is acting along the x direction, that will be tau xz, and this one which is acting along the y direction, that will be tau yz. Now, before we proceed further, I want to draw the figure so that there is 1-2 points which needs to be clarified. Meanwhile, if you have any questions, you can ask me.
Sir, plane and direction of
Ji.
this can be same or not? Like it can be two axes.
Your voice is distorting. I cannot hear you clearly. Can you write a message? लिख के question पूछना, because I cannot hear you properly. Just a moment. Set the plane. No. Okay, let me clear this. Your question. This is basically this. When both the subscripts will be same, it is normal stress, not the shear stress. Okay, now these ones, these are your normal stresses. These are my normal stresses. ठीक है जी? This is my, these are my normal stresses. Sigma xx, sigma yy, sigma zz. ठीक है जी? So in this case, the plane, plane and the direction, they are the same. So they will be your normal stresses. Now come to the shear stresses. You have seen that on each face there were two shear stresses were acting. ठीक है जी? And if we simplify or if we write down those stresses, it was basically tau xy, tau xz, tau yz, tau yx, tau zx, tau zy. So these were the six shear stresses basically which are acting on the three faces of the element. Now, if you see this tau xy, it is complementary. So this tau yx is basically complementary of this tau xy stress. So if you can calculate the magnitude of tau xy, you can know the magnitude of tau yx, which is complementary to tau xy. Similarly, tau xz, the complementary shear stress of tau xz is tau zx. So if I calculate this tau xz, I can get the magnitude. I can also get the magnitude of tau zx. Fine.
हैं?
Moreover, if I
तो
can
भाई
find
यार
the
खा रही है,
magnitude of tau yz,
खा दो,
I can get
खा रही
the
है।
magnitude of this complementary tau zy. Now, the point to be noted here that if we can calculate these three shear stresses, we can get the magnitude of these three shear stresses as well, because these three shear stresses are complementary to these shear stresses. So in actual on three-dimensional element, there are three normal stresses and there are three shear stresses. ठीक है जी? On any three-dimensional element, there are three normal stresses and three shear stresses. This is complementary shear stress of this tau xy. Tau zx, it is complementary. Opposite shear stress means the magnitude will be same, but the sign will be opposite. So tau zx is complementary of tau xz. Tau zy is complementary of tau yz. ठीक है जी? So it means in actual there are three normal stresses and three shear stresses. Is this point clear, guys?
Yes, sir.
If it is clear, then I'm going back to the slides. Now we will read what they are saying. Now, the general state of the stress, triaxial. Triaxial means three axes, x, y, and z. We are going to explain this figure now. The general state of the stress, triaxial at a point, is characterized by total 6 normal and shear stress components. And as we have seen, as we have pointed out that there will be three normal stresses and there will be three shear stress components. So now read this. Is characterized by 6 independent normal and shear stress components which act on the faces of an element of the material located at the point. So this general state of the stress or the triaxial state of the stress, however, is not often encountered in engineering practice. ठीक है जी? Instead, engineers frequently make approximations or simplifications of the loadings on a body in an order that the stress produced in a structural member or mechanical element can be analyzed in a single plane. Now, see this. These are three faces. ठीक है जी. We have said YZ plane, XZ plane, XY plane. ठीक है जी. Now, if I can simplify this figure, moving from three-dimensional to two-dimensional, means if I consider just two axes, one plane, X and Y plane. ठीक है जी. X and Y plane. So then the plane state of the stress biaxial. The plane state of the stress biaxial, where there will be two axes, let's say X and Y axis, at a point is represented by, point is represented by, now if two normal stress component and one shear stress component, which act on the four faces of the element. We will discuss this figure in a short while. So I will just repeat about this. The general state of the stress, which is triaxial state of the stress, is not often encountered in engineering practice. Instead, engineers frequently make approximations or simplifications of the loadings on a body in an order that the stress produced in a member or mechanical element can be analyzed in a single plane. Now, basically, we are converting or simplifying over cases from triaxial state of the stress to biaxial state of the stress. In the biaxial state of the stress, there will be only three stress components, unlike triaxial state of the stress where there were six stress components, three normal stress components and three shear stress components. In biaxial state of the stress, there will be two normal stress components and there will be one shear stress component, which will act on all the four faces of the element. Let's see this figure now. Now, this is, we are moving from triaxial state of the stress to biaxial state of the stress. In biaxial state of the stress, there are only there are only two axes, let's say X and Y axis. So we are not considering this Z axis. Okay? Now you can see this when I consider this plane. Okay? Now you can see this, I am considering only the X and Y stresses in X and Y direction. I am not considering the Z direction. So on this phase, you have the normal stress sigma X, which is acting in the direction of the x-axis, which is acting in the direction of the x-axis. This plane is X, and the direction of the stress is also in the x direction. So sigma XX, it is over normal stress. The shear stress is tau xy because x represents the plane and y represents the direction. So direction is this y-axis. So this is y. No shear stress in the z direction because we have simplified our case from three-dimensional to two-dimensional. Now comes to this one. We have a stress which is acting along the y-axis. ठीक है जी. Plane is y, direction of the stress is y. So this is over normal stress sigma yy. Then the shear stress is basically it should be tau yx, tau yx, which is complementary stress of this tau xy. Is this point clear? And you can see whatever is the stress acting over here, the same is the normal and the shear stress acting on the opposite face. Similarly, whatever is the normal and shear stress, sigma x and tau xy, acting on the front face, the same will be acting on the back face. Fine. So these are complementary stresses. So if I can calculate these value of these stresses, they are acting, their magnitudes are same, only their directions are different. Fine. Now over unknown are sigma x, sigma y. These are the two normal stresses which are over unknown. Tau xy and tau yx. tau yx is the complementary shear stress of tau xy. So basically, I have only one unknown shear stress, that is tau xy. Is this point clear, guys? If you have any question, please ask me. Ji, any question? No question. So it means we have in biaxial state of the stress or plane stress, we have two unknowns. We have three unknowns: sigma x, sigma y, and tau xy. And when I simplified this figure in two-dimensional plane, so I will have sigma y, this one, because now we are drawing the figure in x and y planes. So this is sigma y, this is sigma x, and this is tau xy. Sigma x is the normal stress acting along the x-axis, sigma y is the normal stress acting along the y-axis, and then we have this tau xy, which is the shear stress, tau xy, this one. ठीक है जी, tau xy, and this is the complementary shear stress. Guys, if you have any question, please ask me, because I want to spend some time on it, because now this is the point from where we will start our derivations. So please let me know if you have any queries.
सर
जी,
सर कुछ जो ग्रे में एंड के ग्रे shear stresses है वो भी tau xy y should be.
are you talking about this one?
Yes sir.
जी, this is tau xy, so this one will be tau xy. ठीक है, this is tau yx, this is basically tau yx, so this will also be tau yx. If you see this figure, these stresses, they are acting in one similar way, so basically they are trying to pull the element. ठीक है जी, ये वाले stresses भी pull कर रहे हैं, and they are also in the same direction pulling the element. ठीक है, so actually if you just know this tau xy, the same will be the magnitude of this one with the same you can say sign, because they are producing in what you say the stress in the same sense. This one is the complementary stress, which is in the opposite sense. So if I can find this shear stress, I can know the values and the signs of all these four shear stresses. Similarly, if I can know the value of this sigma x, I can know the magnitude of this. So if you see this figure, they are now telling you that you have only these three unknowns: sigma y, sigma x, and tau xy. So this sigma y, the complementary of sigma y is this one. This is sigma x, the complementary of sigma x is this stress. This is shear stress tau xy, the complementary of tau xy is this shear stress. ठीक है जी? So this shear stress. So if I can calculate sigma y, sigma x, tau xy, I can basically know the magnitude of this stress sigma x, and this shear stress tau xy. So usually, simplification of the loading on a body is done in an order that the stress produced in a member can be analyzed in a single plane. So we have modified our case from three-dimensional element in which we have x, y, and z axis, and we had three normal stresses and three shear stress components. We have simplified to a plane state of the stress, that is biaxial state of the stress, in which there are two axes, x this one, x and y. And correspondingly, we have two unknown normal stresses, sigma x and sigma y, and one unknown shear stress. So we are now showing this on a simple, what you say, two-dimensional element. So this is over plane stress case. This is over plane stress case, which means that it is in two dimensions, one plane. ठीक है जी. So simplification of the loading on a body is done in an order that the stress produced in a member can be analyzed in a single plane. If this would be the case, then the material is subjected to plane stress. Overall case is plane stress, and as the name of the chapter indicates, plane stress transformation, we will basically be working on plane stresses. Our objective in this chapter will be to calculate sigma x, sigma y, the two normal stresses, and tau xy, the unknown shear stress. The state of the plane stress at a point will be represented by two normal stress components, sigma xx and sigma yy, and one shear stress component, tau xy. Any questions, guys? If no question, then we will have a short break. And after the break, we will start with the derivation. We will start with the derivation. So I will restart the class at 10:10. ठीक है जी? Would that be fine?
Okay, sir.
If this book is not opening, I will send you the link from what you say, OneDrive link as well, so that you can download it. The platelet. Guys, can you download this book or not, or are you still facing the issues?
सर बुक डाउनलोड होती है पर ओपन नहीं हो रही।
ओपन नहीं हो रही?
यस सर, वैसे भी सर जो फाइल डाउनलोड हो रही है वो 2700 केबीज की है।
नहीं 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 नहीं, 2000, ये तो फाइल है 78 MB की।
सर
फाइल चलो गुड हो गया। ये तो फाइल 78.5 MB की। वैसे मेरे पास भी ओपन हो रही है। Okay guys, let's start with our lecture, continue with the lecture. Now we will start the derivation. We will start the derivation. I will make few figures and then I will start the derivation. So let me first make the figures and so we will start the derivation. Derivation is basically transformation of the stresses. Like it means that if your element, like this is over plane element, this is my plane element, guys, can you hear me?
Yes, sir.
Yes, sir.
Good. Okay. So this is sigma y. This is sigma y. This is sigma x. This is sigma y. This is sigma x. ठीक है जी. And this one is your tau xy. This is your tau xy shear stress. ठीक है जी. tau xy shear stress. ठीक है जी. And this is your x-axis. ठीक है. And this is your y-axis. Fine. This is regular axis. X-axis, y-axis. Now the thing is, transformation of stresses means that if our axis is oriented at an angle theta with respect to this x and y axis, means our x-axis is somewhere here, y-axis is somewhere here, then how we can calculate transformed stresses, transformed normal and the shear stress. So we will derive the equations to relate the normal stress sigma x, tau xy and sigma y with theta, so that if I put the value of theta, I get the transformed normal stresses and transformed shear stresses. Fine. So let's see this. This done. So this. Now I cut the axis somewhere like this. So this is my new y-axis or y-axis. And 90 degrees to this will be your x-axis. The x-axis will be somewhere here like this. Now let me draw this figure. So I'm drawing this part now. This is your normal stress. This is your complementary normal stresses, and these are your complementary shear stresses. So when I have cut this section from here, y dash axis, I will get this way. Now on this, this is your basically y dash axis like this. Okay, this is y dash axis and this is your x dash axis. This is y dash axis, this is x dash axis. This is your theta Now this theta represents the orientation of this. Basically, if I draw this figure here, this is your theta. ठीक है जी, this is theta. So if this is x-axis and this is your y-axis, this one is your x dash axis and this one is your y dash axis. So this is your theta, which represents the orientation of y dash axis with reference to y axis. This theta and this theta will be same because the angle between the two axes will remain 90 degrees. Okay, now let's say the area of this face, the area of this face is delta A. The area of this face is delta A. The area of this face is delta A. Then we want to know the component of the area along this y-axis and component of the area along the x-axis. The reason is that this is over normal stress and this is over shear stress. Fine. These normal stresses and shear stresses, they are acting along the regular x and y axis. So if this is delta A and this is theta, so this will be delta A. ये क्या होगा फेस? डेल्टा A cos theta. This will be delta A cos theta and this will be delta A. This will be delta A sin theta. ऐसे ही होगा जी. This is your delta A, the cross-sectional area, ठीक है जी, and its component along the y-axis will be delta A cos theta and its component along the x-axis will be delta A sin theta. Do you guys agree with this or not?
Yes, sir.
Yes.
Okay. Now I will make this figure. I should make this figure somewhere here because there will be some stresses. Now the normal stresses which are acting, this is sigma x, this one sigma x. This one is sigma y. This one is your tau xy. This is tau xy. This is also tau xy. ठीक है जी, tau xy. Now if we want to find the forces, with reference to over y dash axis and x dash axis, with reference to y dash axis and x dash axis, with reference to this is my y dash axis and this is my x dash axis. So these are the values of the stresses: sigma y, sigma x, tau xy, tau xy. Fine. Now force is stress into area. Force is, I can write it here, stress is equal to force per unit area. So stress is force per unit area. So force will be stress into area. Is it okay? So force will be stress into area. You have the stresses. Now to convert these stresses into forces, I need to multiply this with the area. So as we know this, that the component of the cross-sectional area about y-axis is delta A cos theta. Component of the area along this axis is delta A sin theta. So I will multiply these two forces with delta A sin theta and this stress with delta A cos theta to convert these normal and the shear stresses into normal and shear forces. Normal and shear forces. So sigma x delta into cos theta, this will be delta A cos theta. ठीक है जी. This will be sigma y delta A sin theta. And this will be delta A sin theta. Everyone agrees up till this point? ठीक है जी. So now we have converted these stresses into the forces with respect to this uh, oriented x dash axis and y dash axis, which are oriented at an angle theta with respect to our regular x and y axis. Okay ji. Now we have these four forces: delta A cos theta into sigma x, delta A cos theta into tau xy, delta A sin theta into tau xy, delta A sin theta into sigma y. So we have these four forces. Now we have to find the component of these four forces which are oriented at an angle, which are oriented about x and y axis, and we want to find their components about x dash axis and y dash axis. We want to find their components.
Cái con gọi là
So
بس اهم بيتصرف اهم بيتصرف مش من ولا
guys, please draw these figures along with me because I will rub this now.
sì, la mia scuola sti
This is your x and y axis. ठीक है जी. Now I will draw x dash and y dash axis. Let's say this is my x dash. Just a moment, please. This is your y dash axis. This is your x dash axis.
क्लास लेना फिर
Is this clear? X dash axis, x axis, y dash axis. Fine. Now let's take forces one by one and find their components. So now we have, first I am taking this force which is tau xy delta A sine theta. So this force is this one, let's say this one. ठीक है जी, this is force tau x y delta A sine theta, delta A sine theta. So it's two components about y dash axis. Its two components about y dash axis is this one, and about the x dash axis is this one. ठीक है जी. Guys, the arrows, please make sure that you have correct directions of these arrows, because later on you are going to sum up by taking the summation of the forces about x-axis and y-axis for the calculation of sigma x dash and sigma y dash. So this was your tau xy delta A sine theta, and I have resolved this force into its two components about y dash axis and x dash axis. Now now the next force I have is sigma y delta A sine theta. Now this force is this one. And this force is acting downwards. So sigma y delta A sine theta. So its components will be this will be its component along y dash axis, and this component will be along x dash axis. Agree? Agree? If you have any issue with the arrow, please let me know. Everyone understands how I am putting these arrows? If you have any confusion in making the vectors, always remember one thing: AB plus BC is equal to AC. AB plus BC is equal to AC, and you can place the arrows in the right direction. You can consider this one as 90 degrees. ठीक है जी, इस point को 90 ले लो. Similarly here, this point should be considered 90. So now after this, I will resolve this force delta A, sigma x delta A cos theta into its components. So this is this force sigma x delta A sigma x delta A it's not writing this. ठीक है जी. So this is now this force. I need to resolve this force into its component. Guys, if you find any difficulty, do let me know. Guys, can you hear me? Guys, can you hear me? आप लोगों को समझ आ रहा है इस? Are you guys getting this force resolution into its components or not?
Yes sir, समझ आ रही है.
Good.
Yes sir.
ठीक है जी. So sigma x delta A cos theta, I have resolved it into its components about x dash axis and y dash axis. So the last one remaining is tau xy delta A cos theta. Tau xy delta A cos theta. ठीक है जी. So in this way we have resolved all the four forces into its components. First, what we have done, we have converted our stresses into forces, and those forces were acting along x-axis and y-axis. Then we have transformed those forces, or you can say resolved those forces into their components along x dash axis and y dash axis. ठीक है जी, into their components. Now next step is now let's come transformation of this orientation of an element to an element having a different orientation. So basically this is x-axis, this is y-axis. So normal stress sigma x, normal stress sigma y, these are the two normal stresses acting along x and y axis, and you have this tau xy shear stress tau xy. ठीक है जी. Sigma x, sigma y and tau xy, they are oriented along the x, and whereas now you have transformed axis is in angle theta. This is angle theta. So x dash axis is oriented at an angle theta with similarly your y dash axis is oriented at angle theta with respect to y axis. Now the transformed normal stresses acting at transformed axis x dash axis, they are x dash and sigma y dash. Sigma x dash and sigma y dash, and this shear stress is transformed shear stress is tau x dash y dash. Tau x dash y dash. Fine. So sigma x dash, sigma y dash, and tau xy x dash y dash oriented along the x dash axis and along the y dash axis represent the same state of the stress at a point. ठीक है जी, so it's a biaxial stress state. So imagine you know the two force components. So what we have done, we have multiplied these stresses with the areas, respective areas, to convert the stresses to the forces. And then we will resolve these forces into their components about x dash axis and y dash axis. Now, imagine you know the two force components, that is summation of forces about x axis and summation of forces about y axis, that will give a resultant force. Similarly, we will find the summation of forces about x dash axis and y dash axis, that will give us the same resultant force Fr. Now, if the state of the stress, so this is now what we have already done in a simplified figure. So this is x-axis, this is y-axis, this is x dash axis, this is y dash axis, which is oriented at an angle theta, ठीक है जी. So the transformed normal stress is sigma x dash acting along x dash axis sorry, sigma y dash transform normal stresses acting along y dash axis, and tau x dash y dash transform the shear stress. If the state of the stress is known for a given orientation xy axis, ठीक है जी, you were given a state of the stress, like state of the stress means you were given sigma x, you were given sigma y, you were given tau xy, ठीक है जी. So if the state of the stress sigma x, sigma y, and tau xy is known for a given orientation xy axis, then they can be means transformed normal and shear stresses can be calculated along any other orientation, that is, let's say along the x dash and y dash axis, which are oriented at an angle theta with respect to x and y axis. So you can see this x dash axis is oriented at an angle theta with respect to x, y dash axis is oriented at an angle theta with respect to y. So over here, our objective is to find the state of the stress for some other orientation. So our objective is to find the transformed normal and shear stresses which are about x dash axis and y dash axis. ठीक है जी. So stresses can be calculated assuming cutting the section along x dash and y dash axis at an orientation theta and then applying the equilibrium equations. So we have x-axis, y-axis, we have sigma x, sigma y, tau xy. This is over transformed axis, x dash axis and y dash axis. So we have cut the section along the y dash axis. First we will cut the axis along y dash axis and we will get the expression for sigma x dash. In the second half we will cut the section along the x dash axis and we will get the expression for sigma y dash and applying the equilibrium equations. So to determine, so this part we were doing to determine sigma x dash and tau x dash y dash. ठीक है जी. section the original element at an angle to explicitly show the surface on which the required stresses are acting. So this is the figure. This is the actual axis, x and y axis. X dash and y dash axis are your transformed axis. X dash and y dash axis are your transformed axis. ठीक है जी, which are at an angle theta with respect to x axis and y axis. Now this is when you will cut the section about y dash axis. This is the area. ठीक है जी, arbitrary area. So the component of the area about y axis and x axis is delta a cos theta and delta a sin theta. Why we are calculating the component of area about uh, y and x axis? Because over normal stresses are oriented, normal and shear stresses, they are oriented with reference to x and y axis, and we have to calculate the transformed normal and shear stresses which will be oriented at an angle theta. So we resolve these, not resolve, we have just mentioned out these forces now. So this is your tau xy delta a cos theta, sigma x delta a cos theta. This is tau xy delta a sin theta. This is sigma y delta a sin theta. These forces I have not mentioned. These are basically your resultant forces transform sigma x dash into delta A, tau x dash y dash into delta A. Transform normal and shear forces along the transformed x dash and y dash axis. Now, in the first part, what we will do, we will we have resolved these forces into their components, I just need to write these two forces as well, and then we will, what you say, we will do this. We will find the summation of the forces about x dash axis. We will find the summation of the forces about x dash axis. So let's go back to our whiteboard. So about this we will have this will be basically your sigma x dash. This is the stress, sigma x dash, and to convert it into force we will multiply with the area, sigma x dash with delta A. So here along the y dash axis it will be tau x dash y dash, and to convert this stress into force we will multiply with the area delta A. Finding now we just have to apply summation of forces about x dash axis and summation of forces about y dash axis. So when I will represent this, it is basically here. This is your sigma x dash into delta A and along this it will be tau is this clear, guys? Tau x dash y dash into delta E. Okay, now we will just use this figure, ठीक है जी, and I'm going to delete this figure. So summation of the forces, summation of the forces fx dash is equal to 0. Summation of forces about fx dash should be 0. So let's start. Sign convention is the same. The forces acting towards positive x-axis will be considered positive. Forces acting towards the negative x-axis will be considered negative. And the forces acting downwards, ठीक है जी, they will be positive. Sorry, downwards is negative, upwards positive. So let's start. So the first force is this sigma x delta A. So this is acting towards positive x-axis, so it is positive sigma x dash delta A. Sigma x dash delta A. Then let's start from here. इसके साथ करते जाएं. So next one is tau xy delta A sin theta. Tau xy delta A sin theta. So along the x-axis you have this component. ठीक है जी? Along the x-axis you have this component. So this is acting away from the x-axis. So this will be negative. So this will be minus tau xy minus tau xy delta A sin theta into क्या होगा जी, what will be the component, whether it will be sin theta or cos theta जी, what will be the component? It is cos theta, this one. Okay. Next one. Sigma A, this sigma y delta A sin theta. So this one again, this component, this one again acting towards the negative x-axis. So negative sign. So sigma y delta A sigma y delta A sin theta, and the component will be this one. ये क्या होगा जी, sin theta. Okay, then comes sigma x delta A cos theta, and the component is this one. ठीक है जी, again towards negative sign. So this will be sigma x delta A sigma x delta A cos theta, sigma x delta A cos theta, and this component will be cos theta. Okay. Last one will be this tau xy delta A cos theta, and the component will be this one. So tau xy delta A, tau xy delta A, tau xy delta A cos theta into component will be this one. ये क्या होगा? Sin theta. And the sum of all these forces should be equal to 0. ठीक है जी? Sum of all these forces will be 0. Now summation of forces. Now summation of forces about y dash axis is 0. Summation of forces about y dash axis is 0. Okay. So first one is this one, tau x dash y dash delta A acting upwards positive. Okay. Next one we can take tau xy. Last time we started from, we are moving this way clockwise. Tau xy delta A sin theta. So this is its component and it is acting upwards and it is positive. So plus tau xy delta A, tau xy delta A sin theta, and component will be, क्या होगा जी component for this one? Sin. Fine. Then you have this one. So the component is this one, acting downwards. So this will be negative. So this will be negative. So component will be sigma y delta A sin theta, and the component will be sin theta cos theta, correct. Okay, next is sigma x delta A cos theta. So this component is again positive. So plus the component is sigma x delta A sigma x into delta A into cos theta, and the component कौन सा होगा जी? This one. ठीक है जी? This one, so this is क्या होगा sin theta?
Yes.
Okay. Next is this tau xy delta sorry tau xy delta a cos theta. It is acting downwards, so this will be negative. So tau xy delta a tau xy delta a cos theta and the component will be क्या होगा जी cos theta ही होगा बेस ही होगा
Yes, sir.
cos theta and the sum of these two should be equal to 0. ठीक है जी. So tomorrow we will continue from here. I will download these figures. So we will continue from here. Tomorrow what we will do, we will simplify these two equations. We will simplify these two equations and we will get our final equation for the calculation of the transformed normal stress sigma x and transformed shear stress tau xy. And then afterwards we will cut the section from plane x dash axis and we will redo all this. We will redo all this. Okay guys, please do not leave the meeting. Let me download your attendance and let me stop the recording. Guys, questions about this, I will take it tomorrow and I will also share these photos with you because in the recording usually they don't save what you say, whatever you have written on the file. Just guys, tomorrow we have class at 9 o'clock. Is it so? हमारी कल क्लास 9 बजे है ना?
Yes, sir.
Inshallah, we will continue with this from here tomorrow. So thank you very much for your time for today. At the start of the class, the number of students were 30, but then it increased to 37. But at the end, again, I am having 31 students. Okay, guys, thank you very much for your time, and I will see you tomorrow again at 9, and I will take up your questions tomorrow as well. Thank you.